It's a degree level concept. So we will come to it. Now, the thing is that although these are very general, where this A, B, C are coming from some fields instead of the field of real numbers, even those types of systems of linear equations and results about their solution, they also find application somewhere, even in some real world problem, like in data security, cryptography. So everything, these things are very interesting. I tell you, you think of these things as not very interesting and boring because you are only seeing the ABCD. You haven't seen the novels. I mean, these are just the beginning of everything. Learning the alphabet, for example, if you are learning English, then learning the alphabets is definitely not the most exciting part of your learning experience. Once you learn the alphabets, then you start to form the words. Then you learn to form sentences, then you can write paragraphs, and eventually you can write a story or you can write a poem. So to get to those parts, we have to pass through these things. So this I can tell you with certainty that no matter how dull these things look, eventually they get more and more interesting as you go higher and higher, further and further, deeper and deeper into mathematics. Things get very interesting, and this is one of the interesting parts. This belongs to algebra, higher algebra. We will come across this. But now back to what I was saying. So that is one problem which somewhat distinguishes between pure and applied mathematics. Let me show you another problem which comes from geometry. We already know how to calculate the area of a rectangle. If this is the length is A and breadth is B, then area equals A into B. This is a standard result from plane geometry, Euclidean geometry, that we have come across, and we in fact use it in our everyday lives while calculating area of some piece of land which is rectangular, or for example some piece of furniture. Now look at this. Suppose I pose this question: find the area of the region below. Now this is a highly irregular shape. It can arise, for example, this can be the shape of a lake, or this can even be a piece of a land, for example, a field, a golf course, something. So you need to find the area, or if this is a golf course, then things will be somewhat different because golf courses are not plain. Anyway, so we are considering here a plain region which is perfectly flat. However, the edge is irregular. Now there is no known formula for calculating the area of this at once. So what do we do in this situation? Unlike the previous problem where the job of the applied mathematician was easy, he or she knows exactly that they need to use the theory of linear equations to solve that problem. So there the job was easy. Here, however, it's not that easy. So one way of attacking this problem is this. What you can do is, we can, instead of trying to find the exact area, let me denote the exact area by A. Suppose there is one value, some value of exact area which we don't know. We try to approximate this exact area by doing something like this. What we do is we cover the inside of this region using rectangles. Using some rectangles, we try to cover the inside of this region. This of course does not go out. It's not supposed to go out. You get the point. Now here we have got how many? 1, 2, 3, 4, 5 rectangles. So let me number them. 1, 2, 3, 4, 5. For each of these rectangles, we can clearly find the area. Take the length, take the breadth, multiply them together, and the product is the area. So for each of these rectangles, we can find the area. We can then add them up. That will give us a value. Let us call that value A1. You can clearly see that A1 will be less than A. Why? Because some parts have been missed by us. These parts have not been accounted for. We have not been able to cover the area using rectangles perfectly due to its irregular shape. So what do we do? The figure we have got is less than the actual area. Although it is somewhat close to the actual area, can we make it better? Of course we can. But how? Let us see. So now what we try to do, we try to draw more rectangles. Let me first fix this small inaccuracies. Okay. So why introduce more rectangles? That is because we want to capture parts of the missed areas. For example, here we can draw another rectangle. Here, for example, we can draw another rectangle. Here we can draw one more. Here we can draw one more. Here also. Here, here, and here also. Here we can draw 2. So now the number of rectangles has increased. You can see that still we are missing some parts. But now if we include these extra rectangles and count their total area up, add that to A1, we get a new area A2, which is definitely greater than A1 because we have more rectangles. But it still stays less than A because we have missed some parts of the total area. If you keep on doing this process by including even smaller and smaller rectangles, you can understand that you will start getting closer to the actual area. So you see that unlike the previous problem, here there is no best fitting pair of shoes. Here there are many shoes which progressively get better and better. This can be, we can in fact make a best pair of shoe, and the best pair of shoe, in trying to do so, we invent a part of calculus that is called integration. We will come to that later. But we see that in this way we can attack the problem. It need not be the case that there is only one pair of shoes like the system of linear equations that we encountered in the previous problem. There can be a sequence of pairs of shoes. Now, so here, what is the applied part and what is the pure part? The pure part, of course, is already available to us, area of a rectangle. We know how to calculate that. The applied part here, however, is much difficult to decide how many rectangles and in what type of way the rectangles have to be taken so that our area measurement comes as close to the actual value as we want. So this is the other situation, that is the applied part. Now, what have we achieved by considering these two problems so far? Let us come to that. That is in fact the main matter here. You have noticed that both the problems that I have presented to you actually arise in the real world. So is it always the case? Do all